Okay, dear learners, today we shall be constructing a cubic spline interpolating polynomial. Okay. A cubic spline is a piecewise polynomial that satisfy the following conditions. The first one being S of x is a cubic polynomial, or we can say is a polynomial of degree less than or equal to 3. Further, the second condition is our S of xi is equal to yi. That is, it satisfies all the nodal points, the conditions on the nodal points. That is, we are given the points x1, y1, x2, y2, and so on up to xn, yn. So the cubic spline interpolation S of x should satisfy all these nodal conditions. Okay, and the third one, our S of x, S dash of x, and S double dash of x are continuous, and in each interval it is going to be a continuous because it is a polynomial, but it should be continuous in the entire interval a comma b, where a is our x1 and b is our xn. So the simple base thing we use here to construct such a polynomial is, since S of x is a cubic polynomial, so this implies when you differentiate a cubic polynomial twice, it becomes a linear polynomial. So S double dash of x is a linear polynomial. Let us denote S double dash of xi to be mi, where I is equal to 1, 2, 3, etc. up to n. So now, in each of the subinterval xi minus 1 comma xi, S double dash of x is a linear polynomial which is going to be the straight line equation joining the points xi minus 1 comma S double dash of xi minus 1 and xi comma S double dash of xi. So which is given by the 2-point formula. S double dash of x, it is S double dash of xi minus 1, which is nothing but mi minus 1 plus S double dash of xi mi minus S double dash of xi minus 1 mi minus 1 divided by xi minus xi minus 1 into x minus xi minus 1. So on taking LCM and grouping the terms, we have xi minus xi minus 1 into mi minus 1 plus mi minus mi minus 1 into x minus xi minus 1 divided by xi minus xi minus 1. Now group the mi terms and mi minus 1 terms. So on collecting the mi terms, we have xi minus xi minus 1 minus x plus xi minus 1 into mi minus 1 plus, and then the mi terms, x minus xi minus 1 into mi divided by xi minus xi minus 1. So cancelling out the terms and simplifying, we have s double dash of x is equal to xi minus x into mi minus 1 plus x minus xi minus 1 into mi divided by xi minus xi minus 1. Now integrate this twice because we are interested in finding s of x. So integrating twice. Integrating the above expression twice, we have s of x is equal to, in the first term, xi minus xi minus 1 is a constant. Then integrating xi minus x twice, we have xi minus x the whole cube by 6, and this mi minus 1 is a constant. In the similar manner, we can have it here. If you integrate xi minus x once with respect to x, we have xi minus x the whole squared by 2. So on integrating again, we have, of course, by minus 2. So integrating again, we have xi minus 1 minus x the whole minus 3, so by 6. In a similar manner, double integrating x minus xi minus 1 twice, we have x minus xi minus 1 the whole cube by 6. Mi minus 1 and mi are constants. And this s double dash is a linear polynomial. So s of x is a cubic polynomial. So on double integrating, the linear factors will turn out to be the 0. Okay, so the constant terms, the constant of integration will be a linear polynomial. Xi minus x and x minus x I minus 1. So this is the required cubic spline interpolation in the interval. This is true in the interval. This will be the interpolating polynomial in the interval xi minus 1 to xi. So now our problem turns out to finding the constants C1 and C2. Of course, we should also need these mi values. So we have to find C1, C2 and mi. To find the constants, arbitrary constants C1 and C2, we can apply the initial conditions. We know that S of xi is yi. So applying for the case of I minus 1. So we have S of xi minus 1, it is equal to xi minus xi minus 1 the whole cube into mi minus 1, because this factor turns out to be 0, xi minus 1 minus xi minus 1. So 6 into xi minus xi minus 1 plus c1 into xi minus xi minus 1. So cancelling out the common factor, our aim is to find the c1. So divide throughout by xi minus xi minus 1, and we know s of xi is xi minus 1 is yi minus 1, and dividing by xi minus xi minus 1, we have xi minus xi minus 1 into mi minus 1 plus c1 by 6, of course. So from this we get c1 equal to minus of xi minus xi minus 1 by 6 into mi minus 1 plus yi minus 1 by xi minus xi minus 1. So we got C1. Now apply the boundary condition. S of xi equal to yi. Also, S of xi is equal to, now in this formula, if you substitute x is equal to xi, the first term will go off. So from the second term we have xi minus xi minus 1. Xi minus xi minus 1 the whole cube by 6 into xi minus xi minus 1 into mi. Right? And the next term c1 into xi minus xi, that vanishes. So we have c2 into xi minus xi minus 1 plus c2 into xi minus xi minus 1. So now dividing by, we know s of xi is yi, and divide the equation throughout by xi minus xi minus 1. So we have yi by xi minus xi minus 1 is equal to xi minus xi minus 1 by 6 into mi plus c2. So from this we get c2 is equal to minus of xi minus xi minus 1 by 6 into mi plus yi divided by xi minus xi minus 1. So substituting these two constants c1 and c2 in our s of x, we have s of x is equal to one by xi minus xi minus 1 into xi minus x the whole cube by 6 into mi minus 1 plus x minus xi minus 1 the whole cube by 6 into mi, substituting the value of c1. c1 is minus of xi minus xi minus 1 by 6 xi minus xi minus 1 by 6 into mi minus 1 plus yi minus 1 by xi minus xi minus 1 into xi minus x plus substitute c2. c2 is minus of xi minus xi minus 1 by 6 into mi plus yi divided by xi minus xi minus 1 into x minus xi minus 1. So now we just collect the terms. Collect the cube terms and then the mi minus 1 terms and the yi minus 1 terms. So we have this is equal to 1. Here we can have the first terms can be had in this manner. xi minus x the whole cube into mi minus 1 plus x minus I minus 1 the whole cube into mi divided by 6 into xi minus xi minus 1. Now collect the mi terms. Mi minus 1 and mi terms. We have xi minus x. So it is minus 1 by 6 minus 1 by 6 into xi minus xi minus 1 into xi minus x into mi minus 1 plus x minus xi minus 1 into mi. So we have collected the mi minus 1 and mi terms. Now grouping the y terms. So it is plus xi minus x into yi minus 1 and x minus xi minus 1 into yi divided by xi minus xi minus 1. So this gives the cubic interpolating polynomial for any x in the interval xi minus 1 and xi. So now if you are able to find this mi minus 1 mi, or simply we can say if you are able to find this mi, then the problem is over. So our aim is to find, our problem now reduces to evaluating mi for I is equal to 1, 2, 3, etc. up to n. For this, we use the continuity continuity of s dash of x. So using this this guarantees that continuity of s dash of x in the interval a comma b, where a comma b is divided into the subintervals x1 to x2, x2 to x3, and so on up to xn to xn minus xn minus 1 to xn. Those n minus 1 subintervals. And in those subintervals, our s dash of or we can say, suppose s I minus 1 of x is the piecewise interpolating formula for every x in xi minus 1 to xi. Then we should have s I minus 1 of xi should be equal to, or s I minus 1 dash of xi should be is equal to s I dash of xi. Only then we can say s dash of x is continuous, where our I varies from 2, 3, etc. up to n. So we have those n minus 2 conditions. So first suppose that s I minus 1 dash of xi. For that let us write down what our s I minus 1 of x is equal to. That is s of x in the interval x I minus 1 to xi. So it is the same function. It is nothing but xi minus x the whole cube into m I minus 1 plus x minus x I minus 1 into mi divided by 6 into xi minus x I minus 1 minus 1 by 6 into xi minus x I minus 1 into xi minus x into mi minus 1 plus x minus xi minus 1 into mi plus xi minus x into yi minus 1 plus x minus xi into yi divided by xi minus xi minus 1. And we have s I of x. So this recurrence relation, from this recurrence relation, we can have s I of x is equal to xi plus 1 minus x the whole cube into mi. Just replace I by I plus 1. So x minus xi into mi plus 1 divided by 6 into xi plus 1 minus xi minus 1 by 6 into xi plus 1 minus xi into xi plus 1 minus x into mi plus x minus xi into mi plus 1 plus xi plus 1 minus x into yi plus x minus xi plus 1. Yes, small mistake over here. This is xi minus 1. So it should be x minus xi into yi plus 1 divided by xi plus 1 minus xi. Now we know that si dash of si minus 1 dash of xi should be is equal to si dash of xi. So si minus 1 dash of xi should be is equal to si dash of xi. So from this we get that if you substitute xi here it will be 0. So we go for this term. Of course this should also be whole cube. So differentiating this once we have 3 into xi minus xi minus 1 the whole squared. Mi is a constant by 6 into xi minus xi minus 1 minus 1 by 6 into xi minus xi minus 1 into differentiating this term once we have minus mi minus 1 plus mi plus. Now differentiating this again once we have minus yi minus 1 plus yi divided by xi minus xi minus 1. In the similar manner we differentiate this si of x once and replace x by xi. So this should be equal to if you put if you replace x by xi minus 1 this factor becomes 0. So this will be on differentiating this will be 3 into xi plus 1 minus x, but we are replacing x by xi, so xi the whole square into mi divided by 6 into xi plus 1 minus xi minus 1 by 6 into xi plus 1 minus xi into differentiating this we get minus 1. So minus mi. Differentiating this we get plus 1. So plus mi plus 1. And in the similar manner differentiating this last term we have plus minus yi plus yi plus 1 divided by xi plus 1 minus xi. So now collect the mi terms to one end and yi terms to the other end. And let us try to simplify. So now pick xi minus xi minus 1 in common. So xi minus xi minus 1 into mi by 2 plus mi minus 1 by 6 minus mi by 6, and these terms we take to the left hand side. So minus of. Here we can pick xi plus 1 minus xi in common into mi by 2, then plus mi by 6 minus mi plus 1 by 6, and we bring the y terms to the right hand side. So it is equal to yi plus 1 minus yi by xi plus 1 minus xi minus yi plus 1 yi minus yi minus 1 divided by xi minus xi minus 1. Now let us group the mi minus 1 terms, mi terms and mi plus 1 terms. So mi minus 1 term, we have only one term. So it is xi minus xi minus 1 by 6 into mi minus 1. Next, collect the mi terms. So this is going to be 3 minus 1 to 1 by 3. So we have plus xi minus xi minus 1 by 3. In a similar way, here there will be one minus sign. I have missed one minus sign here. So it is plus mi. So this becomes minus mi. Or we have, because we have taken minus in common, this becomes minus mi. And this will be plus mi. So minus plus, it becomes plus xi plus 1 minus xi into mi, right? So we can cancel these two terms, and then now collect mi plus 1 term. So it is plus xi plus 1 minus xi plus xi plus 1 minus xi by 6 into mi plus 1 is equal to yi plus 1 minus yi by xi plus 1 minus xi minus yi minus yi minus 1 by xi minus xi minus 1. So now putting in the proper form, write this in the proper form, we have xi minus xi minus 1 by 6 into mi minus 1 plus xi plus 1 minus xi minus 1 by 3 into mi plus xi plus 1 minus xi by 6 into mi plus 1 equal to yi plus 1 minus yi divided by xi plus 1 minus xi minus of yi minus yi minus 1 divided by xi minus xi plus 1, where I varies from 2, 3, 4, etc. up to n. So here we have the n minus, we can't go up to n because we have the index I plus 1. So up to n minus 1. So from this we have the n minus 1, n minus 2 linear simultaneous equations. Equations in mi. But there are n unknowns, m1, m2, etc., mn. If you are able to find all those unknowns m1, m2, etc. up to mn, we can substitute in this spline interpolating formula. But to solve those n unknowns, now we have only n minus 2 linear equations. So we need 2 more equations. So if we take m1 equal to 0, the condition on the m points, and m2 equal to 0, then the resulting cubic spline is called natural cubic spline. So along with this n minus 2 simultaneous equations, on taking m1 equal to 0 and m2 equal to 0 as two other equations and solving these n equations in mi, the resulting cubic spline we call as natural cubic spline. Suppose we know the another boundary condition, that is S of Z1 equal to y1, suppose, or we can't take it as y1, we can take it as y11, and S of Z2 equal to yn2, that is where Z1 lies between x1 and x2 and Z2 lies between xn minus 1 and xn. Then again from this condition we get two more equations in m1, m2 and mn minus 1 and mn, and solving those two equations we can find those along with these n minus 2 equations, combining the two equations we get from here and solving, we get not and not cubic spline. This we call as not a not cubic spline because this x1, y1, x2, y2, etc., xn, yn are called knots or nodes. Nodes are knots, but this z1 and z2 are not the knot points, and we know the condition at those 2 points and we use them to find mi. So they are called not a not cubic spline. There is another case where if we know the first derivative at the end points, so if you know s dash of x1 equal to some value k1 and s dash of xn equal to some k2, then also we have a system of n equations which we can solve. Or the fourth type of cubic spline, if we know s double dash of x1 and that is nothing but our m1 and s double dash of x2 xn, that is our mn, again we get another set of cubic spline equations. So in this session we have elaborately discussed how to arrive at a piecewise cubic polynomial, that is cubic spline interpolation, and the variations in the cubic spline interpolation. Okay, we shall meet in the next lecture. Thank you.